Okay, we've been looking at the fundamental units, and so we're going to continue talking about units, and we want to add in a concept known as dimensional analysis. So we've already seen the 7 fundamental units, and in the SI units, they are the meter, the second, the kilogram, the mole, the Kelvin, the ampere, and the candela. So these are the 7 fundamental units. And of course, we know that meter is a measure of length, second is a measure of time, kilogram of mass, etc. So we've seen what all of these are. And we have symbols that we use to denote these units. And so the meter is a measure of length, and it's represented by the letter M. The second is a unit of time, it's represented by S. The ampere, for example, is a measure of electric current, and it's represented by the symbol A, etc. Now, these symbols are all tied to the SI units, the ones that are the standard for scientific application. But as you know, there are other units. For example, we could measure length in feet or in miles or in furlongs. There are many different units of length that we could pick from. And so we can talk about length as measured in meters, but we could also just talk about length as, what length is. It's the length of something, and we can represent it, we can say that it has a dimension of L. And we differentiate between the symbols representing a specific unit and the symbols representing the generic dimension by putting the dimensions in brackets. And so the standard is for seconds to be measured with a dimension of T, and kilogram, M for mass. The mole there's an N. That actually, the N represents number, which is what a mole is. It's a specific number. The Kelvin, we've already got T used for time in seconds, and so the Kelvin is measuring thermodynamic temperature. That's represented by the Greek letter theta. That's a capital theta. The electric current has a dimension of I, and luminous intensity has a dimension of J. That's a capital J. And of course, the brackets tell us that we're talking about the dimension, the generic idea, rather than the specific quantity, meters or feet or whatever. We just have L for the dimension. Now, we have talked about the fundamental units, the 7 fundamental units. And we said earlier that we can combine those in ways to make more complicated concepts. And so derived units are essentially the units for concepts that are generated by combining fundamental units. What do I mean by that? Let's consider speed. Speed is an example of a derived unit. Now, speed is defined as a distance divided by a time. And so distance or length is a fundamental unit. Time is also a fundamental unit, but speed is not. Speed is a combination of 2 fundamental units, one divided by the other. And so the units of speed would look something like meters over seconds, or miles over hours, or feet per second is the usual way to say that sort of thing. Now, the dimensions of speed would be L over T. And I could write it like this, just the L dimension over the T dimension. But when you divide by something, that's the same as expressing it to the power of -1. So more often than not, we tend to express dimensions in terms of power. So this would be L to the 1 power, that's understood, times T to the -1. That's the same as L over T, but that would be the way that we would normally express the dimensions of something like speed. And the specific units could be feet over seconds or miles over hours or whatever, but the dimensions would just be denoted that way. Now, when you are describing a measurement or describing a quantity in physics, you must always, note that it's underlined and bold-faced for emphasis here, you must always include the units that go along with any measurement. It's wrong without the units. If I ask how long is this thing and you tell me it's 12 something, that doesn't mean anything. If you say it's 12 centimeters, now I know what you're talking about. If you say 12 inches, I know what an inch is. So I can tell you what that length is. I have an understanding of what that length is. But if you just say 12, I have no idea what 12 what is. So if you're taking a class from me, not just watching this video because you came across it on YouTube, if you're actually taking a class from me, you'll find that I'm pretty lenient about a lot of things, but I'm not lenient about that. The units always need to be written down. They're very important, and you just need to be in the habit of including the units, because without the units, it is wrong. Note again, all caps, boldface. Without the units, it is wrong. So include the units wherever they're appropriate. I also want to briefly mention the rule of equality, because this is an important concept. Anytime you have an equal sign, it means the stuff on the left is of the same kind as the stuff on the right. So let's talk about just regular numbers. If I have 7 plus 5 and I say that's equal to 12, that's a valid equality statement. I've got this number plus that number is equivalent to that number. That is the same. If I say that 8 feet, now I've got a unit here, 8 feet is equal to 12 feet minus 4 feet, that is also a valid equality statement, because I've got the same kind of thing on the left, that's feet, as I've got on the right, also feet. But if I say 10 meters per second is equal to 15 meters per second squared minus 5 meters per second, that's not a valid equality statement, because the unit here, meters over second squared, is not the same as meters over second on either side of the equation. All the units in an equation must match. That's very important, and we'll see it's actually very powerful for us in terms of being able to check to make sure that our answers are correct, and also even to be able to sometimes discover new physics by simply looking at the formulas of things. It may seem like a really simple and obvious idea, but it's actually really powerful enough that it was worth mentioning to you. Now, I said in the previous slide that we can use our units to check whether or not we've got our answer right, or at least to eliminate wrong answers. Now, here we have two equations, including their units. So this is an equation we'll see later on in the course. This x represents the position of something as a function of time, and it's 3 meters per second squared t squared plus 4 meters per second t minus 4 meters. If this is a valid equality statement, then all of the units must match. And position is generally going to be in something like meters, so we need it to be meters. Now, what we can look at is what are the t? The t stands for time, and if I look at t squared here, t there, if I consider time being measured in seconds, I would have seconds squared divided by seconds squared, and I would be left with meters. Here, I would have time in seconds that would be divided by seconds, and again, I would be left with meters. Here, I would be left with meters. So if the position on the left is measured in meters, this would be a valid equality statement, because all of these units are equivalent to just plain meters. Now, if I look here, I've got meters over seconds squared times t squared. That's, again, the t is going to be measured in seconds. I can eliminate seconds squared divided by seconds squared. But look here at this term. I've got only seconds here divided by seconds squared. That would have a complete unit of meters over seconds, not meters. And so that unit does not match the meters here or the meters there. So the bottom one would be an invalid equality statement. The units don't match. They must match. And so if you're trying to remember a formula and you don't remember whether the formula should be t squared or t or some other variable, very often if you know what the units of things are supposed to be, you can figure it out just by the process of elimination. So you have to know the units of things, because if you don't include the units in your answer, it's not correct. But you also need to know the units of things because it can help you know whether or not you've misremembered something, or whether you've made a a mistake somewhere along the line. So understanding the units of things, very important, very powerful. Now, we've already talked about how different quantities can have different types of units. So, for example, a length could be measured in meters, or it could be measured in feet, or whatever. Here, we need to be able to convert from one kind of unit to another kind of unit. So if you've measured something in inches and I've got stuff that's measured out in centimeters, how can I bring them together and get them, all on the same page? And that's through the process called unit conversion. Now, some unit conversions are very straightforward. You all know that there are 60 seconds in 1 minute. If I tell you that something is 3 minutes long and I ask you how many seconds that would be, I think every single one of you would be able to do that conversion, probably in your head. Now, there are lots of different types of conversions for different quantities. One that's important is converting inches to centimeters. And so you can look here. Here I have a picture of a scale. If I go out to 1 inch, you can see that it's equivalent in centimeters. If I look, I see 2, 1, 2, 3, 4, 5, and that is just a little bit, not quite to the half between the 5 and the 6. So it's 2.5 something, and it turns out it's actually defined to be 2.54 centimeters. That is the equivalent to 1 inch. And so the inch is actually defined to be this. And of course, we already talked about how the meter and therefore the centimeter were defined. Centimeter is, of course, 1/100th of a meter. So 2.54 centimeters is the equivalent to 1 inch of length. And so if I tell you that something is 6 inches long, if you multiply that 6 by 2.54, that'll tell you how many centimeters that 6-inch long thing is. Now, next I want to look at sort of the process of how we do this unit conversion in sort of a systematic way. So let's look at an example, and this is a pretty straightforward one. How many inches are there in 1 meter? All right, so we want to start with meter, and we want to convert it to inches. And so we need to get rid of meters and have inches left over. Now, on the previous slide, we had our conversion factor. We knew that 1 inch is equal to 2.54 centimeters. Now, what I have here is I've written out the 1 meter, and I know there are 100 centimeters in every meter. So I've just sort of written this way. This is called the ladder method. It doesn't actually look like a ladder, but that's what they call it. So I've got 1 meter. I'm dividing by a meter. Why am I doing that? Because I know that that will let me cross out meters divided by meters, and I'll be left with centimeters as units. Now, if I wanted to convert to centimeters, I would be done. But I don't want to convert to centimeters. I want to convert to inches. And so I know 1 inch is equal to 2.54 centimeters. Now, do I put the centimeters on top or on the bottom? I obviously put it on the bottom because I need the centimeters to cancel, and then I'm left with inches, and that's my final unit. And so basically, you have this equivalent statement. We start out with 1 meter. Then we're multiplying by 100 centimeters and dividing by 1 meter. 100 centimeters is equal to 1 meter, so we're basically, this whole thing is equal to 1. So I'm taking that meter and I'm multiplying it by 1. And then I've converted from meters into centimeters, and then again, I'm multiplying by 1. And so doing all of this gives me the way to do it. So I just basically then go with all the numbers. I take 1 times 100 times 1 divided by 1 divided by 2.54. And of course, you don't have to do the ones. 1 times or divided just gives you what you started with. So I'm going to basically go 100 divided by 2.54, and my units that I'm left with are inches. So 1 meter is equivalent to 39.4 inches. And to get there, all I did was I kept multiplying by 1, but I did it in such a way to make the units cancel out and convert it into the units that I wanted. when you practice this, it gets pretty easy to do. But there's one aspect of it that in the past my students have struggled with a little bit. So, for example, converting areas and volumes is sometimes problematic. We know the conversion between meters and centimeters is that factor of 100. That is, 1 meter is equal to 100 centimeters. But what if I'm converting an area? Well, what a lot of students will do is they'll say 1 meter squared is 100 centimeters squared. And that's the incorrect conversion factor. You can't multiply by 1 if you have something that's not equal to 1. So what you have to do is look at what 1 meter squared is and what 100 centimeters squared is. And so if I look at my square here, I've got a square that we can say is 1 meter by 1 meter. At the same time, because 1 meter equals 100 centimeters, we could also say that that square is 100 centimeters times 100 centimeters. The area of that square has to be the same value regardless of whether we're using meters or centimeters as our unit for measure. So what would be the area if I was measuring in meters? Well, it's just the length times the width, and so that would be the area is 1 meter times 1 meter, and that gives me 1 meter squared. But if I'm using centimeters, then the area would be 100 centimeters times 100 centimeters, and that gives me 100 times 100, or 100 squared, centimeters squared. Now 100 squared is 10,000, so that tells us that 1 meter squared is 10,000 centimeters squared. That is, if you broke this box into little bitty boxes, each a centimeter by a centimeter, there would be 10,000 of them that would fill a meter squared. And of course, this box that I've drawn is way too big for that because I can't draw it small enough. But you could imagine if I drew centimeter square boxes, it would take 10,000 of them to fill up this meter squared. That's the equivalency. And so that's your conversion factor. So let's look at this in practice. Here's another example. A particular machine component has an area of 1.25 inches squared. Now, we know immediately that this is an area, so that's going to be a little bit tricky. We want to know what its area is in centimeters squared. Now, our conversion factor for inches to centimeters is we already know that 1 inch is equal to 2.54 centimeters. If I want the squaring conversion factor, I just simply square both sides, and I know 1 inch squared, I'll square this. If I square the 1 inch, I have to square the 2.54, and when I do that, I get 6.45 centimeters squared. That means 1 inch squared is equal to 6.45 centimeters squared. Now, we started out 1.25 inches squared. We want to know what that is in centimeters squared, so again, we're going to multiply by 1. And we know that this is equal to that, so 6.45 divided by 1, that's the equivalency for centimeters squared to inches squared. And again, this whole thing together is just multiplying this number by 1, but doing it in such a way that the units cancel. And so when you do this, you get 1.25 times 6.45, and you get 8.06 centimeters squared, and that would be your answer for 1.25 inches squared would be equivalent to 8.06 centimeters squared. All right, here's one for you to try. This is example number 3, and it says there are 5,280 feet in 1 mile, and there are 3,600 seconds in an hour. So given these conversion factors, we want to convert 30 miles per hour to feet per second. That is, how many feet per second are there in 30 miles per hour? Now, I want you to pause the video, and really, please do it. Pause the video and try to work this out on your own. And I'm going to work it out for you, but I want you to try it on your own. So please pause the video and do this problem real quick. Let's see what we get. Okay, did you pause the video? Did you try it? What'd you get? All right, hopefully you actually did it and you're not just watching without doing the work. Okay, so I've started out with 30 miles per hour, and there's really a 1 hour that's understood there. You don't normally write it out, but it's 30 miles per hour. And I want to convert miles to feet, and I want to convert hours to seconds, and then that will give me feet per seconds. Okay, so let me go ahead and convert feet to miles, or actually miles to feet rather. And so I know that my conversion factor is 5,280 feet in 1 mile. So where does the mile need to go? The mile has to go underneath in order to cancel with the mile above. So I can say that 1 mile is equal to 5,280 feet. And then when I do that, the miles have canceled. And now I've got, if I just multiplied this out, if I multiplied 30 times 5,280, that would give me feet per hour. But I don't want feet per hour, I want feet per seconds. And so now I have to get rid of the hour and convert it into seconds. And so I know the conversion factor is 3,600 seconds for every hour. Now where does the hour go and where does the 3,600 seconds go? Well, we know that the hour has to go up on top, 1 hour, and that will be equivalent to 3,600 seconds. Of course, this whole block here I'm just multiplying by 1, but I do it such that I've got hours down below and hours up above that cancel, and my units, what I'm left with, are feet over seconds, and that's what I want. So I just need to multiply 30 times 5,280 and divide by 3,600. And when I do that, I end up that this is equal to 44 feet per second. And that is my conversion. How did you do? Is that what you got? Now, if this makes sense to you, great. If you were struggling with this, I have office hours for a reason. You should come visit with me. I'll work some extra examples with you. We'll make sure that this is solid. This is a pretty straightforward thing. Some people find it a little bit tricky at first, but once you get it down, it's really easy. It just takes a little bit of practice. So if you're struggling with this at all, please come let me help you. All right? So anyway, we'll go on to the next video.